Oh, hi. So today we're looking at these properties of exponential functions, different traits that you're going to see all exponential functions having, and how they connect to some of the important variables of the exponential functions. So we know that exponential functions can be expressed like this, and today we're going to be taking a look at adding this value c to an exponential. And here are some things that you're going to notice. Exponentials grow in one direction and decay in another. So they either look like this, they either look like that, where they grow in one direction, or they decay like that. And you would say they would be growing in that direction if we went that way. Okay? So they either do one of those two things, and that has to do with one of these numbers, a, b, or c. They also have an initial value, and just like the y-intercept of a line, knowing the initial value of your exponential is important for graphing purposes, but it's also important to understand a situation. Like if we're looking at a population that's growing exponentially, and I told you that its initial population was 1 million, well, that's really significant to the situation we're looking at. So that's an important factor to think about. And then the last factor that all exponentials have is an asymptote. An asymptote, like if I have an exponential function that might look like this, well, it's probably approaching but never quite equal to that line. So an asymptote, just to review, it's a math vocabulary. This is not a part of the function. It's actually one of the restrictions on the domain or range of your function. When we looked at the reciprocal function last unit, that was a function that had a vertical and a horizontal asymptote, a number that it could never reach, but as it approached it, it had interesting behavior. The exponentials have a horizontal asymptote only. They have no vertical asymptote, but a horizontal line that they will approach but never touch. So when you're graphing exponentials, this is a really useful table of values that you can use to graph your exponentials. So just looking around 0 is really valuable. So if you have no other clues, start looking at these values, and you might look at those values and say, I could expand that a little bit in some cases, but in a lot of cases this is useful. Other times, in different applications, maybe you're looking at the population of a city over the course of a century, in which case you might take x values of 25, 50, 75, and 100. You might have different values that are suggested to you by the application situation. But if you're doing a purely algebraic example, definitely take a look at the behavior of the exponential around 0. And tomorrow, when we look at the full transformed versions of exponentials, the d value would also give you some clues on some other x values to choose. But this is generally where I would start. So the graphing investigation that I'd like you to do is to graph all of these on your whiteboards and then transfer the graphs to your notes once you've verified those graphs in Desmos. Now, I'm going to do an example for you, and I'm going to show you how I graph using that table of values. So here we go. And I'll pause the video for this because I'm going to do this on the whiteboards. Oh, sorry, on the whiteboard up at the front. So here we go. Here's Desmos. And I'm going to make Desmos match kind of what you're looking at, where I see values of x sort of minus 10 to 10. So that's pretty good right there. And y values up to about 15. Okay. And now, and down to about 15. So this is the whiteboards in portrait mode, so where the longer side is along the y-axis. And that's generally more interesting for exponential functions because they have that really vertical behavior. And so now the one that I'll graph for you will look like, let's say I have 2 to the x. I'm just going to turn this off so I can surprise you all. But I'm going to multiply that by 3. And then I'm going to subtract, let's say, 8 from it, let's say. Okay, so now I'm going to go ahead and make a table of values here. Someone's got to give me a marker. Someone gets an excuse to throw stuff at me. Throw it up. Great. So, I've got to just pause the video here because this won't. All right, so here are all the different functions. And if we take a look at m of x here, let's see why we should not be surprised by that graph. So the first part that we notice, take a look at the c value. C value of 10 there. It never touches 10. It's approaching 10 from the inferior side, and it's getting closer, closer, closer to 10.
The range would be like y.
Yeah. You would say y is up the reals, and 10 is greater than 1. So that's our range for m of x. That's the range for m of x. It approaches 10 but never equals it, so we don't need less than or equal to. We just need, well, 10 is greater than y, or y is less than 10. Y is less than 10 would get the style points. That would be a little better than that. Okay. What? Oh, yeah, sure. Yeah, let's hear it. Huh? Why? Oh, here. There. So that's what it sounds like.
You gotta make it a circle. It's so weird when you do a circle.
Oh, we'll have different harmonies and stuff?
It like cuts into like 4 different sections. Just try it.
Okay, fine.
Y equals, or hold on, I have the equation. So y
I defer.
equals. Okay, but it has to be 0.005.
What?
Okay, do 200. Weird, right?
Okay, so this now just became the maybe the most off-topic video we've done in class. But anyway, this is what I want to take a look at here. Let's look at this exponential function where we just have an a, a b, and a c. Why, Lexi? So with this one, if I set my b to something like 2, my a to 1, and my c to 0, this is just here f of x, right? It's the same function. And then if I start changing a, what's going to change? The asymptote, the initial value, or the direction of growth? Stretch factor. So as I decrease a, the initial value goes down. As I increase a, the initial value goes up. There's a is 10. Notice my initial value 10. And connect that in your mind to the exponential growth and decay that we looked at, where a was the initial value, and you can pull it out of word questions and pop it in there. And then that's going to create these exponential growth situations. Let's set a back to identity, set it back to 1. And then, what happens as I change b? What do you think? Actually, look at c first. Let's show this line y equals c. If I increase c, it increases the whole shape. So c corresponds to what feature of the graph? It's changing the y-intercept, certainly, and you will find that a plus c is your y-intercept. A plus c. A is kind of the distance above the little dotted line. What's the name of that little dotted line? The asymptote. Even if we're decay, so I'm going to set this b to decay there, it's the c value is still the asymptote. And then I set the b value for growth, it's still the asymptote. And the speed at which we approach the asymptote is related to the size of b. Now here's b is less than 1. Here's b is greater than 1. Yeah, and it's the line that the exponential is approaching in one direction. Okay, so here when b is between 0 and 1, what kind of situation do we have? What's the name for this kind of situation here? Is it exponential growth or exponential decay? This is exponential decay. And then as b is greater than 1, we have exponential growth. Right. So b determines the direction of growth and the speed of growth, because that's your growth factor. And besides that, that's your a, b, and c. So that shows you the relationships between these variables and the initial value, the direction of growth and rate of growth, and the asymptote of these functions. So you can now answer in your package what the numbers a, b, and c do to these different things here. And then carrying on, general properties for y equals a multiplied by bx plus c. Well, the domain, we've noticed that x is real numbers. We even know how to make negative exponents now, and fractional exponents, and decimal exponents, and raising things to the power pi. So you can do it all with x. It can be any number. Of course, there will be limitations on your domain in different application situations. If a social media campaign starts tomorrow and starts growing exponentially, it doesn't make much sense to look at negative values of x, because that's like before the social media campaign started, how many views did it have? Right? What does that even mean? It's like 0, of course. The range, well, the range is still y is real numbers, but y is less than or equal to c, or y is greater than or equal to c. Okay? We will have situations where my y values, let's make c 5 or 4 or something like that. Okay? And then with my, if I look at the possibilities for this graph, y is never less than 4. It's never even equal to 4. If I go back that way, it says it's 4, but it's just because it's so darn close to 4, it's rounding to 4. It's still 4 or bigger. So in this case, y is greater than 4. If my a value is negative, then y is less than 4. And there is a limitation on the range. We don't ever cross the asymptote, or we don't reappear on the other side of the asymptote the way a reciprocal function will. An exponential function is just bound by that asymptote, down or bound up. So you take a look at the a value, that will tell you the limitations on your range. The y-intercept is a plus c. If c is 0, it's very clear to see that the y-intercept, here, let's make a 1, and let's make c 0. And in this case, we're going to see that the y-intercept is there 1, right? As I increase c, that's increasing the y-intercept, so let's make c 10. Okay, now the y-intercept will be 11. But if I now decrease a, like I make a negative 10, notice that a plus c is still giving me that y-intercept. If a is less than that, let's say it's 4, here it's going to be 6, right? Oh, whatever, it's going to be 6.2. There, 6.2. It's a plus c. Ooh, yeah, kind of does. And then x-intercept is, who knows? Go find it. These functions can have an x-intercept only when you have a c value that makes an x-intercept possible. So if I look at this one, here's the x-intercept. It's a weird decimally number. I could find it graphically. I could find it by guess and check. But that's it. And you'll find it algebraically next year when you learn about logarithms. But if I start changing b or something, it changes the x-intercept. You see these have x-intercepts here. But if I make c less than 0, no x-intercept anymore. Doesn't matter what I do to this number here. Oh wait, yeah, if a is positive, now I got an x-intercept again. If b changes, I can change the x-intercept. But that one is just like a go find it. There's no real rule. Who knows? You go find it. What's the asymptote? Y equals c is the asymptote. That's very useful knowledge. Keep this knowledge for tomorrow. Y equals c is the asymptote. It's very direct, very straightforward, and should be very intuitive. So far, we've only looked at examples where c is 0, and we always had the x-axis as the asymptote. As you add or subtract, it's just a vertical translation, so it also moves the asymptote along with it. So in your package, you can use your new knowledge to associate these different graphs with the different equations. And then here is a quick lesson on determining. Actually, I'm going to save this for tomorrow because I didn't do this with the morning. So we'll start here tomorrow and then look at transformations of exponential functions. Thanks for showing up for your learning, everyone. And thanks also for listening to Weird Decimos Graphs. I'll show you some others.